Okay.
Good afternoon, everyone. My name is Kendall Belcher, and this is my presentation on seismic requirements for building design. By definition, seismic refers to the scientific study of earthquake and the propagation of elastic waves through Earth. An earthquake is the result of a sudden release of energy in the Earth's crust that creates those seismic waves, and this wave can be generated by a sudden dislocation of segments of the crust, whether it's a volcanic eruption or event made by man-made explosions. And you look at the picture right here. What you will see is a seismograph that was used about 200 years ago. And what you see right here is a seismograph more currently used, where it basically reacts to the vibrations, and then the ball reacts as a pendulum, and then the pin juts down the wave. And if you look over there, this first P wave is referred to as the primary wave. It's going to be the longitudinal wave, and it's going to be the fastest. And it's going to be the one that appear first. And after you're going to have the first S wave and then the surface wave. And those waves will act as shear waves. Causes of earthquakes. Earthquakes are caused by disruptions in the tectonic plates. So what would happen is, at this point, you would have the tectonic plates reacting with one another. And that would create a seismic wave that will spread across the surface, and that will create a fault plane. And the three types of faults to expect are a strike slip, a normal, and a thrust. This right here is a Richter scale that measures the magnitude of an earthquake from 0 to 10. As you can see that if it's from 0 to 2, it's a micro earthquake, and we have about 8,000 of those happening per day, because you're generally not going to feel those. And you get to about 5 to 6, you have about 800 occurring a year, and they're going to be moderate. But once you get to 10, these are massive and have never been recorded so far. And they are extremely rare since they haven't happened. And in the recent history, the largest earthquake occurred in 1960 in Chile. It had a magnitude of 9.5. And the largest earthquake by depth toll in the 21st century occurred in 1976 and had a depth toll from 200 to 600,000. But the largest earthquake overall in history was in the 16th century, and they estimate that about 800,000 people died in it. And the largest earthquake in the last 2 years was in Japan, where it had a magnitude of 9, and it was the largest earthquake that Japan had in their recorded history. So as you can tell, that you may not have earthquakes of these great magnitudes happening all the time, but they still happen. And so that's something that we must consider. Now, if you look at the picture on the left, you can see there's a dam. And this dam was composed of thousands of tons of cement and concrete and had a bunch of reinforcing steel in it. But yet the effect of the earthquake, no matter what magnitude, still caused that type of failure to occur. So these earthquakes can cause severe problems to happen, even to the strongest and most heavy of structures. Over here, you can see an earthquake that affected the city, and if you look over there, you see a couple of bystanders observing the effects of all the earthquakes. And then you look up here, down here, you see some innocent-looking children, because in a situation like this, they're not necessarily going to be going to those people first, because those people are deceased. So they wasn't going to try to help the living people that can possibly still be helped. This picture right here has the effects of an earthquake if you're looking at it along the streets, where you can see rubbish through all the streets and several buildings impacted. This image right here, and this one shows the effect that it has on the street, where it causes the levels to rise up and down from different thrust and normal falling that occurs. And if you look at this one, you can see the effect of a landslide, which is a byproduct of an earthquake. And then over here, you can see a building that's falling is now being supported by another building, as you have the military walking the streets. This is a study that was computed by an organization called CATDAT, where they took 7,000 earthquakes from 1900 to 2012 to measure the direct economic loss. And if you look, you can see that 70% of the damage, of the $2.2 trillion damage, is going to be from the shaking of vibrations alone created by the earthquake. And then you have 14% 14% that's going to occur from fires. And fires are a very, very prevalent thing that happen because you can have an earthquake causing the building to vibrate, and it can cause an electronic device to malfunction to just create a spark, and that spark can start a fire. And the highest followed by that is going to be tsunamis. This right here is the damaging earthquakes per country in 2011. And if you look at the scale down here, you will see that most of the earthquakes occurred in Japan, followed by China, followed by Turkey, India, the Philippines, and then countries like America and Alaska. But you will notice that if you look at Africa, only one country was affected by it. And you look at Canada, not really was affected by earthquakes. So those are not generally earthquake-prone regions. If you look in this area and this area, those are located in the Pacific Rim, known as the Rim of Fire, and those are active plate boundaries, so you have about 95% of all earthquakes are going to occur in that region. Building codes. The one to your left, the design of multi-story reinforced concrete buildings for earthquake motion by Bloom, Newmark, and Corning was like the pioneer work on earthquake design in 1960. It was created by the Portland Cement Association, and it was like the first case to actually analyze how you go about designing a building for earthquakes. And they analyzed it from a scientific approach. And the opening quote in the preface of the book says that earthquake-resistant design is not rigid enough yet to be mathematically or design codes or procedures alone. You still have to treat it as an art as well as a science. And those words were as true then as they are today. The other three codes you are familiar with, the International Building Code, the minimum design loads for buildings, and the Building Code for Structural Concrete. The ICC Building Code was the first one to address really seismic design, recently in 2000. And it created a thing that was known as SDC, seismic design categories, that help categorize the level of type of seismic risk your building is going to be prone to. And here it goes right here. It has those comparisons between what different codes use. So in ACI, they refer to the SDC as AB for low seismic risk, C for moderate seismic risk, and DEL for high seismic risk. And these are something that are mandatory to do by the ICC, and they are directly used to help determine the maximum height of a building and the method of analysis for the building. Seismic coefficients. This is directly from the 2011 Masonry code that we use, and they pulled it from the 2000 IBC. And what it basically tells you is, it uses the SDC design criteria, and it helps you to figure out what your modification coefficients will be, but it also helps tell you your height limit. So for instance, you're working with ordinary plane pre-stress. Your response modification coefficient is 1.5, your system overstrength factor is 2.5, your deflection amplification factor is 0.25, and as far as the seismic criteria A or B, you have no limit on your height restriction. But for C to F, it is not permitted to be allowed in code. As Angela stated earlier, the maximum height is going to be allowed to be 35 feet. This right here is a graph that they use to go about in designing. So what you have right here is this is going to be the capacity of your material, and this right here is going to be the nominal capacity, and that difference between those two are your reduction due to ductility. Ductility means something that you want to be having in the materials that you use. If they were brittle, they would fail instantly. And this one right here is going to be the design that you would design for. Seismic forces. The seismic force is determined from Newton's second law, F is equal to ma, where F is your force inertia, and then you have your mass on your acceleration. So objects that have a greater mass are going to have a greater force of inertia. And that creates a problem because that means you have greater lateral forces that can cause your columns or your beams to fail more likely. And because of this formula, that is why a lightweight construction is generally going going to be preferred in highly seismic areas. Fundamental period. This is one of the most important parts when it comes to analyzing a building for seismic design, because what you have is a period is just how long it takes for something to go a full cycle, and then the inverse of that is frequency. And so what the fundamental period is, it's just the natural vibration rate that an object will vibrate if you hit it. Every object will go about it. And so they will advance from the first mode to the second mode and to the third mode. And as your buildings get taller like this, they will go through several modes that you have to analyze and look at. But when you're just dealing with first or fourth-story buildings, you can just look at the first mode, the fundamental period, because that's generally going to be the most effective one, the one that's going to most likely happen first. Seismic design factors. The 6 factors that you generally consider when you design are torsion, and torsion is basically like a rotation. And at an object center of mass, you're going to have a rotation will not be occurring. So what you try to do is get the center of mass and the geometric mass to align with one another, but that's generally going to be unavoidable. So you're going to have that natural eccentricity, and you still want to keep the torsion down to the minimum because that can create other problems. And then you have damping. And damping is just your natural vibration absorption occurring by your different building materials. And as the one I mentioned earlier is ductility. Ductility is the ability of your material to bend or to flex, but yet to not deform too much. And that is what you want in these buildings, because if they were very brittle, as soon as these forces hit it, they would instantly start to break, but instead they are able to flex and bend more to react more to the forces. And then you have strength, and strength is the object's ability to withstand the applied loads and to be durable. And stiffness is just its ability to resist deflections, to stay rigid as possible. Building configuration is a big important part when you're designing these, because if you use things that are regular, that are talked about more in the code, that are generally standards in practice, you will have a greater likelihood of your building resisting failure. And here are some examples of regular and irregular configurations. Like T-beams, L-shapes, and U-shapes. Those are different configurations that are going to be used common. That's why it's more favorable to use like your shear walls, your brace frames, and your moment-resistant frames, because you know exactly how the loads are going to transfer. You know how they will react to the loads, and it's more like knowledge on the subject matter in the field. Seismic design strategies. The 6 strategies you're going to be able to look at, you can look at your diaphragms, your shear walls, your brace frames, your moment-resistant frames, your energy dissipating devices, and your base isolation. Since the other 4 were talked about in the earlier 2 presentations, I'm going to focus on the bottom 2. Energy dissipating devices are helpful because whenever these forces hit the building, you have a bunch of energy being dissipated throughout the structure. And depending on the magnitude of going to different locations, it can cause failure, whether at the joint or any other location. So one thing that they encourage you to do is, if you're designing like a moment frame connection, make it eccentric. That way energy is dissipated and you are altering the load transfer. But it is still not as effective as it could be. So what they now encourage you to do is to put in an energy dissipating device that will help take some of that energy. And that will help sustain the life of your building a lot more. And another thing that I thought was cool is that you have something called base isolation, which is where you basically have it so your base and your building are separated. And so that when these ground motions out and forces start happening, your slab will be flayed, but your building will be staying vertically erect. And this is something that is good to do, but you cannot use it for high-rise buildings because the building won't be able to act as rigid as possible. And the higher it goes, the more likely the moment can overturn it, and that will be a big problem. And this right here is a concentric brace frame where it meets at the point, and this is the eccentric brace frame that they encourage you to do. This right here is some examples of non-structural damage control. Like you have parapet walls, chimneys, stacks, suspended ceilings, and elevators. And these are all other criteria that you need to consider when you're designing a building, because you can have an earthquake happen and a shaking cause one of these to fall or collapse. You could have a fire that could cause problems. And so this is something you need to consider. Design. The 3 steps you go about when you're designing is first you analyze the site conditions. You look at the soil. You look at if there's any type of utility connection, like a utility door anywhere. You want to analyze that so you know what area you are working with. And then you want to establish Seismic design objectives as far as are you trying to be A, B, C, or D. So you can go from there. And then lastly, you want to select and design the appropriate structural systems by choosing the best material and going about doing the best and most optimal design. These are my references. I use the textbook, the 2011 code, the designer's guide, and these 2 links. Any questions?